Hi everyone, my name is Amy Priest. I'm a tutor here at REACH. I tutor chemistry classes, and today we're going to be talking about conjugate line diagrams. These were introduced in chapter 55, and they are so incredibly important in all of your acid-base chemistry problems. So what is a conjugate line diagram? I have one written up here, and bear with me, I know it's backwards, but hopefully you can get the general idea. So a conjugate line diagram shows, typically it starts with an acid and shows its dissociation. So to refresh, we have, for an acid, we have H3PO4. A really good way you can tell that you're working with an acid is if you have an abundance of hydrogens. Because remember, an acid is a proton or a hydrogen ion donor. So here we have 3 hydrogens. So I can already tell that this is going to be a polyprotic dissociation, meaning it can go through multiple dissociations. So going through this diagram, we have H3PO4, we move to H2PO4, so it's acted as an acid, and this is equivalent to its Ka1. So Ka is your acid dissociation constant. Typically just tells you what is our number, like how good of an acid is this step. So we're going from our Ka1 to make H2PO4. H2PO4, we still have a hydrogen, so now it can lose another hydrogen, become HPO4 minus, and it has a corresponding Ka2. Finally, we still have one more hydrogen that could be given away, so we can go over to PO4 minus, and that step is called the Ka3 step. So notice I also have Kb steps at the bottom. So anytime you're looking at a conjugate line diagram, it's always easiest to write it starting it as an acid. So start with your parent acid and go through all of the dissociation steps. And anytime you do that, then your acid steps will be read from the left to the right, how I just did. But we can also look at how it would act as a base. We always look going from the right to the left. And another way you can tell that this is a base, we have no hydrogen, so it can't, like it just physically cannot act as an acid. And it also has a 3 minus charge. Anytime you have a minus charge, that's going to strongly probably be a base, because it can, that minus charge is saying that it can accept hydrogens, which have a plus charge. So here we have PO4 3 minus. It can gain 1 hydrogen with a corresponding Kb1. HPO4 2 minus can go and gain a second hydrogen, H2PO4 minus, giving that a Kb2. And then H2PO4 can still act as a base and gain another hydrogen with a Kb3. So notice how these are related. You can go from H3PO4 to H2PO4, and that's an acid step with Ka1. Or if you do the reverse, H2PO4 to H3PO4, that's corresponding to Kb3. So it's really important to write all of these out step by step to make sure you've assigned your Ka and Kb values to the right spots. So like looking at an example, let's say, because you may not be working with this whole entire conjugate line diagram. Say you're working through a problem that's dealing with the dissociation of HPO4 2 minus going to H2PO4 minus. So looking at what's happened here, we started out with just 1 hydrogen and we've gone to 2 hydrogens. So that's telling me that this is acting as a base, a hydrogen acceptor. So that means we need a Kb value. And sometimes you might not, you have your appendix in the back of the book, but sometimes they may not give you exactly what you're looking for. But luckily you have this relationship. Ka times Kb equals Kw. And as a reminder, Kw is the autoionization constant of water that's introduced in chapter 54 or so. And Kw, though, is equal to 1.0 times 10 to the negative 14. and it will always be equal to that. So what this relationship gives you is if you know, we always know KW, and if you know either KA or KB, then you can find the other one. So for this particular problem, let's say we don't know our KB, but we would know our KA, which that is given in the back of the book, but I will not go into assign numbers for this problem. So let's assume we do know our Ka. So we can look back up, find this portion of our reaction in our conjugate line diagram, and I see that HPO4 minus going to H2PO4 minus, it's using these two values. So our Kb for this reaction is technically your Kb2. And we know if we're trying to find our Kb2, we can do Kb2 equals Kw, still 1.0 times 10 to the negative 14, divided by our corresponding Ka2. And then that will give us our Kb value. So these diagrams are incredibly important to understand because you're going to be doing a lot of problems with them, and you want to make sure that you know which KB or which KA am I using, and if I don't have it, how can I find it? So take a look, do some practice in chapter 55 and onward. You'll use them for several of the acid-base chapters. And if you still have questions, you can come see us in our office in Strickler 111, or you can find us online at reach1.louisville.edu. Thank you for watching.